Today is the first lecture. I'm a little bit jumpy because I have a new laptop, and for reasons that I do not understand, the files on my laptop are different than the files I expected. There's something very strange going on with synchronization. But I think I have the right ones. The plan for me, my schedule, is that I do the final preparation for the lecture on Wednesday morning, and that means that I upload the slides essentially half an hour before the lecture starts. So if you're in the habit of downloading slides the night before, as some people do, to take notes, they will be slightly different, right? Not a lot different, because I'm essentially working from past slides. It's not that. They will be very different, but there will be slight differences. So I'm going to do two things today, because the introduction was done yesterday. I'm going to talk about the science of climate change, and I'm going to talk about scenarios. Come in. Now, this is an economics class, so I won't examine your understanding of the physics, I won't examine your understanding of the biology or the chemistry of climate change, but it is good to understand this. If you want to solve a problem, you need to understand the problem, because that's the only way of solving it. Even though all of you have picked up some things about climate change from the media, unfortunately that is not a reliable guide to anything. You can read and hear and see any amount of nonsense about climate change in the media. From the Earth will explode because of climate change, which is a paper that really has been published in a genuine peer-reviewed journal, to climate change is a Chinese hoax by the former president of the United States, and anything in between. And this is unfortunately not limited to sort of the fringes of the internet. Also supposedly quality news outlets such as The Economist or the BBC or The Guardian or The Times very regularly get it wrong. The most common mistake that you will hear in the English media is that climate change is somehow a threat to the survival of humankind, which is complete nonsense, or that climate change is a threat to human civilization, which is not as complete a nonsense as that humanity will die out, but it's almost there, right? So you can hear any amount of nonsense on the internet, and that is why I start with just getting everybody on the same page so that we have the same understanding of how the problem actually works. So today I'm going to talk about, or before the break, I'm going to talk about the greenhouse effect and the enhanced greenhouse effect. I'm going to talk about observed climate change, general circulation models, and projected projections of climate change. And then after the break, I'm going to take a bit of next week, what was scheduled for next week, and talk about scenarios of emissions, and therefore scenarios of climate change as well. So that's the plan for today, and let's start with the enhanced greenhouse effect and observed climate change. So you're looking at 9 graphs here. Let's start at the, for you guys, left. I'm the sort of person who can't tell left from right, or up from down, or plus from minus. So always be careful when I say that you need to add something, you may want to subtract it. But left and right is a fundamental problem for me as well. So on your left, what you're looking at are the atmospheric concentrations of the three most important anthropogenic greenhouse gases, that is carbon dioxide, CO2, methane, CH4, and nitrous oxide, N2O, over the last 10,000 years. So this is from the start of the agricultural revolution. And what you see is that and obviously these are reconstructions, not observations, and what you see over that period is that concentrations were roughly constant, and then at the start of the Industrial Revolution you see that they begin to skyrocket. They essentially asymptote to what seems like infinity. Now this is a graphical illusion. These smaller insets show the same reconstructions and observations of the atmospheric concentrations since the start of the Industrial Revolution over the last 250 years or so. And what you see is that the concentration doesn't asymptote, it doesn't skyrocket, but it only increases exponentially. Right? Now on the right hand side you're looking at the global mean surface air temperature, average sea level, and for the world as a whole, and snow cover on the northern hemisphere. And these are observations. And what you see is that the temperature has gone up, that sea level has gone up, and that snow cover has come down. And these observations on the right hand side are perfectly consistent with the observations on the left hand. And the reason for that goes back to an old bit of physics. And that is the description, the workings of the natural greenhouse effect. I'm pausing because I'm forgetting a name. So this is how it works. We have a cartoon here, not drawn to scale. This is planet Earth. That is the sun, right? In reality, the sizes are a bit the other way around. The sun emits lots of energy, and a lot of that comes in the visible part of the spectrum. Most of that energy goes to outer space, but a small fraction of that energy happens to hit planet Earth. So that is the first thing that you see. Some of that solar energy is reflected at the top of the atmosphere, some of it is reflected at the surface of the planet, and some of it is absorbed by the planet, right? This cannot be the end of it, right? Because if the planet would absorb energy and absorb energy and absorb energy and does that for millions and tens of millions and hundreds of millions and billions of years, then the planet would have long evaporated, right? It cannot be that we're just absorbing energy. There has to be an equilibrium. But the Earth does not emit energy in the visible part of the spectrum, right? At night, the ground does not light up. If it does, you have smoked something that perhaps you should not have, right? Instead, the Earth emits energy in the infrared part of the spectrum, right? And that goes into outer space. That is the initial direction. But in the atmosphere, there are so-called greenhouse gases. Now, by definition, a greenhouse gas is a gas, obviously, that is transparent to visible light, but opaque to infrared radiation. So if a ray of solar light hits a CO2 molecule, it passes right through. If a ray of infrared radiation hits a CO2 molecule, the CO2 molecule absorbs that energy and gets, as a chemist would say, excited. Now, that cannot be the end of the story either, because if these CO2 molecules would just be absorbing and absorbing and absorbing infrared energy, they also would have long fallen apart. So a short while after the CO2 molecule has transited into its excited state, has absorbed the infrared radiation, it re-emits the infrared radiation. And it goes back to its base state. Now that re-emission of the energy of the infrared radiation can be in any direction. It can be that the CO2 molecule emits its infrared radiation into outer space, but it can also send the energy back to planet Earth, where it gets reabsorbed by the planet and then later on re-emitted. So this is the natural greenhouse effect. Damn it, I still don't know the name. Because of this, it is harder for energy to leave the planet than to enter the planet. And as a result, more energy is stored on planet Earth than it would be had there not been greenhouse gases in the atmosphere. And as a result, there's more energy on the planet, and therefore it is warmer, right? This is old physics. It was Jean-Baptiste Fourier who first discovered experimentally in the 1830s, no, in the 1820s, 1827 he published this, that having an atmosphere actually warms up. Just having air around just warms up the planet. Later calculations showed that had it not been for the atmosphere, the temperature, the average temperature of planet Earth would not be the current plus 15 degrees, but would be minus 15 degrees Celsius. Minus 15 average temperature. That's very, very cold, right? And this is still the natural greenhouse effect. It was Planck who figured out that it was not just air, but it was CO2 in the air, again experimentally, and I'm terribly sorry that I forgot her name. This was an experiment that was done in the 1850s, widely ignored. Everybody commented on the fact that she was a woman, rather than the fact that she had discovered that CO2 heats up the planet. And then John Tyndall, 5 years later, described the physics, did the theory behind the observation. What is her name? Sorry about this, I should have looked this up. And then it was Svante Arrhenius in 1896, the later Nobel laureate Arrhenius, who first noted that if you put more of CO2 in the atmosphere, then the logical implication of the natural greenhouse effect is the enhanced greenhouse effect. If you have more CO2 in the atmosphere, then the planet will get warmer. Right? So this is old physics. If you don't believe me, or if you don't believe the physicists, there's plenty of videos on YouTube where you can actually do the experiment that shows that CO2 has a heating effect, and you can just figure it out for yourself. This is very basic science. So the first order principles are very, very simple. So if you put more CO2 in the atmosphere, which we have done, as you can see on the left-hand side, the planet will get warmer, right? So this is an update of the previous slide I showed. Land surface temperatures go up, sea surface temperatures go up, the temperature of, so this is the temperature of the water, this is the temperature of the air over the water, sea level goes up, sea ice goes down, temperature higher up in the atmosphere goes up, temperature lower down in the ocean goes up, humidity goes up, and I'll talk about this. Glaciers go down, snow cover goes down, right? All of this is perfectly consistent with the very basic principles, very basic, essentially 19th century physics will tell you, well, these are the signs that we would expect. But there's all sorts of complications going on here. One complication is that the anthropogenic greenhouse gases go up. Anthropogenic stands for human-made. But we always have to put in this qualifier, anthropogenic, because there's also natural greenhouse gases. And the most important natural greenhouse gas is water vapor. It's actually a much stronger greenhouse gas than CO2. And there's a lot of it in the atmosphere. Now the problem is that we also have the law of Clausius-Clapeyron, and that says that warmer air can contain more water. So if the temperature goes up, you would also expect humidity to go up, right? And if humidity goes up, there's more water in the atmosphere, and that means that you have more natural, you have more H2O as a greenhouse gas in the atmosphere as well. So this is what is known as a positive feedback. Positive in the sense that it strengthens the signal, not positive in the sense that it's good. So you have the initial warming caused by more CO2 in the atmosphere that is then strengthened by the feedback mechanism of having more water vapor in the atmosphere, right? So that is one complication. If you have more water in the atmosphere, you also have, presumably, more clouds. Now, clouds are complicated things. But you all know the basics of what clouds do to temperature, right? On a summer day, when it's cloudy, it's cool. And when the clouds are not there, it gets very hot. That is, the clouds keep out the energy of the sun. But in winter nights, if it's overcast, it's actually rather mild. Whereas if the clouds are there, if it's overcast, they actually keep the heat in. Whereas if the clouds are not there, the heat escapes and it gets much colder, right? So depending on the time of year and depending on the time of day, and also depending on whether there's dark clouds or light clouds and whether there's low clouds or high clouds, clouds have different effects on the temperature, right? And obviously, as temperatures change and as humidity changes, you would have different patterns of cloudiness that may strengthen the initial signal, but may also weaken the initial signal, right? So this is a feedback mechanism that is rather unclear. And there's a lot more complications in the atmosphere going on. So what people have done is build so-called general circulation models. These are the second most complicated models built by humans. The most complicated models are the models for protein folding, but the second most are climate models. And essentially what climate models do is they work through all the mechanisms that are going on in the atmosphere and in the ocean, on the surface of the planet and on the ice sheets, and figure out what would happen if we increase the concentration of CO2 and other greenhouse gases. What are all the feedback mechanisms that come into play? And solve those equations. Some of it's are based on physics, some of it's are approximations of the physics, and try to figure out what would happen to the climate, what would future climate be like. And I've given you one complication in these models. There's other complications as well. What you're looking at here is, again, observations. On the very left, we're looking at observed warming from 1850 to 2019. Now what you see is that the planet has warmed 1.1 degree, something like that. And then here we're looking at the decomposition of this. So this is what we have observed. This is what the models say should have happened. Well, you see that the models are not bad, right? And then here that is broken down into four major components. These are the greenhouse gases. This is aerosols, mostly. So we did not only put CO2 and methane and nitrous oxide in the atmosphere, we also put lots of dust in the atmosphere. And those dust particles have two effects. One, they directly scatter sunlight, so send sunlight back into outer space, and that's a cooling effect. But they also help form clouds, because clouds don't just appear. Clouds need condensation nuclei, little dust particles, around which the water condensates and then forms a droplet, right? That is where clouds come from. Clouds don't appear in pristine sky. The net effect of these things is mostly negative, but then there's other stuff going on. The sun isn't constant. And we have a very conservative, very chaotic system, so there's also internal variability where there's still overhang from the ice ages and so on and so forth. Right? So that is this bit, and this bit here is then further broken down into what are the greenhouse gases. We have carbon dioxide, we have methane, I mentioned that, nitrous oxide, we have the halogenated gases, particles, more particles, these are aviation contrails, so this is not the CO2 that comes out of aeroplanes, but this is the water vapor that comes out of aeroplanes. That also contributed to warming. And then these negative effects are also split into sulfur dioxide as one of the particles and a bunch of other things. The one that I did not mention yet explicitly, but I did so implicitly. Some of the solar energy is reflected at the surface of the planet, which depends, as you may have guessed, on the properties of the surface, what we actually do with the surface. And you know the answer to this, right? In summer, what you want to do is wear light clothes, because if you wear white, the solar energy is reflected off you and you don't get hot so much. If you wear black in summer, you heat up, right? Now, what is true for you and your clothes is also true for the planet. Not that we put a light or a dark jacket on the planet, but one thing we have done, for instance, is replace forests, burn them, cut them down, and have grassland instead. Now, if you look at a map, actually, forests are typically dark green and pastureland is light green. If you look down from a plane, forests are actually dark green and grassland is light green. So if you replace dark forests with light grassland, you actually absorb less energy, right? Similarly, if you replace grassland with concrete, then you absorb more energy. Or if you replace grassland with asphalt and tarmac, you actually absorb more energy, right? So there's also things going on at the surface of the planet. Physicists call this albedo, that also may have a cooling or a warming effect, right? So there's all sorts of things going on. And then there is, of course, the carbon cycle itself that matters too. So I'm going to talk about CO2 because that's the most important greenhouse gas. It's definitely not the only one. But let's look at what CO2 actually does in the atmosphere. So this is another cartoon. There is a lot of numbers and a lot of things going on in this graph. The two things that you should keep in mind that are most important is that circles denote stocks. This is the amount of CO2 that is somewhere. And then the arrows are flows. That is CO2 moving from one stock to another stock, right? Then in yellow, we're looking at how things were in 1750. And we call that natural. not natural at all, but let's call it natural. And then in, I want to say purple, but you may want to say pink, we're looking at how things have changed since the start of the Industrial Revolution. Right? So, what is going on? Let's start here in the middle. So, this is essentially what humans have done, right? Fossil fuel emissions, 2 years ago I think, we put 9.4 petagrams of carbon per year into the atmosphere. A petagram is 1 billion metric tons. It's a lot of stuff that we put into the atmosphere. And since the start of the Industrial Revolution, we actually took out 445 petagrams of carbon from the soil. Essentially fossil plant material in the form of coal, oil and gas. We dug it up, pumped it out and burned it. And that led to an increase. So we took 445 out, and it led to an increase in the atmospheric stock of CO2 of 279. Right? There's plenty of coal, oil and gas left in the ground, so we burned 445. These are the reserves, not the resources. Reserves are the stuff that we know where it is and we know how to get it out profitably at prices in 2019. I should not say current prices. So there's plenty more to be dug out, right? That is what these numbers mean. Now, this flux of 9 petagrams of carbon per year, where does that go, right? Because obviously there's something missing here. We emitted 445 and the atmosphere increased by only 280. So something else is going on. And that something else is what is going on in the terrestrial biosphere. So what plants do is photosynthesize. And if plants photosynthesize, they take CO2 from the air and use that to make stems and leaves and flowers and what have you, seeds and roots and everything. That is gross photosynthesis. And the annual uptake through photosynthesis of CO2 is around 140 petagrams of carbon per year. But that happens mostly in spring and summer. And then now we're entering fall, and the leaves are falling and plants are dying back. And a lot of that CO2 is released back into the atmosphere. And that release back is around 135 petagrams of carbon per year. You may wonder, why is this? Well, most of the land is on the northern hemisphere, so you really see a seasonal cycle in what's happening on land, right? Now, some people get confused by this, right? Natural emissions are 110, human emissions are 9, so we are trivial, right? How could we have changed the climate if our emissions are 9, less than 10% of natural emissions of the terrestrial biosphere alone? The reason is very simple. Here is a flux that's going up, here's a flux that's going up, and a flux that's going down, right? That is the big difference. Yes, it's true that human emissions are small relative to natural emissions, but natural emissions are largely offset by the opposite, by absorption, right? And actually the nature is helping us, because the downward flux has increased by 29, the upwards flux only by 26. So the terrestrial biosphere, this is the greening effect, because there's more CO2 in the atmosphere. Plants, forests are growing faster and bigger, and also storing more CO2 in the soil, right? That's also where a lot of CO2 is stored. This is a biological effect. There's a chemical effect going on in the oceans. where because of the laws of partial pressure, if there's more CO2 in the atmosphere, then there must also be more CO2 stored or dissolved in any water body that is in direct contact with that atmosphere. Right? That's just the passing of the gases. And what you see is that the oceans take up around 54 petagrams of CO2 per year and emit during winter time about 55 naturally. And then these fluxes have also increased because of the increase in the atmospheric concentration of CO2, right? So we emit 9. Of that 9, 3 disappears into plants and around 2 disappears into the ocean. Which means that annually we add about 4 to the atmosphere, right? That is how to read these numbers. Now, this is a simplification of what is really going on. It is much more complicated. This is again part of those general circulation models. They have all this included. And the important thing here, the important complication is that this is biological action, right? This is plants growing and trees growing, which obviously depends on how much rain falls on them and what is the temperature. So these processes are not independent of climate. If climate changes, then plant growth changes as well. And actually the same is true for the ocean chemistry. If temperature changes, then ocean chemistry changes as well. So this is another feedback effect, right? So by now we have a very complicated system, right? The initial signal is simple. We have more CO2 in the atmosphere and therefore more energy would be stored on the planet. But that initial signal gets strengthened by more water vapor, and then it gets altered by more clouds forming, and then it gets altered by changing how CO2 is cycled over different parts of the carbon, different parts of the planet. And it gets very, very, very complicated, right? So the first thing, time is actually right here. The first thing you may want to do is, do I trust these models? Right? The first thing you want to do is say, oh, do these models have any predictive skill? And I would not be standing here if they had not, right? This is a faint picture, right? You guys in the back cannot see the light blue and the light pink, right? So this is a product of the Intergovernmental Panel on Climate Change. This is the latest results, blah, 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 blah. And one of the things that they do is put ever more information on a single graph. What am I looking at? Let's focus on this one here. No, let's focus on this one here. This is the global mean surface air temperature, the one at the top in the middle. The black line that you see, and you see very clearly also in the back, is the observed temperature. Right? It's sort of like going up and down and then it started rising. Now there's 2 other lines, one that you see and one that you do not. The one that you can't see is in dark yellow, orange, brown type of color. And that is model predictions of what the global mean surface air temperature would be if we start the model in the year 1850 and just let it run unconstrained. Just feed in actual emissions, but don't strain it with observations of what the temperature was. And then what you don't see is the range around that, because it's too faint. That's in pinkish. And what you see is that actually the brown line hides behind the black line. That is, if you take the average of the 45 models or so that have done this, then they almost exactly predict, altogether, almost exactly predict the observed temperature increase. That builds some confidence that these models are not completely crazy. This is true for the global mean. This is true if you focus just on temperature over land. This is almost true if you focus on the heat in the ocean. It's true if we look only at North America or only at Europe and North Africa. So this seems to be okay. It's not just that we get the global mean right, but also the regional pattern. So that is one set of experiments that is run. The other set of experiments that was run is that they used the same models, but instead of feeding these models with the increase in CO2 emissions and other greenhouse gases, we just put in the natural forcings. So just volcanoes and just the sun and internal variability, and that's it. But no anthropogenic greenhouse gases. And then you end up with the dark green line that may appear black in the back. That's the average across the 45 models or so that did this. And then the faint green bars around it, the faint green area around it is the range of models. And what you see is that if you don't allow for human forcing of the climate, then the observed temperature is actually outside the range of expectations. True in the global mean, again true at all continents. Let's look at where we are. So this is the predicted warming or the predicted climate without anthropogenic forcing. This is the range. And then this is the observed. And actually what you see is that over the last 20 years or so, we are well outside the range of expectations without greenhouse gases and other things in the atmosphere. And this is not a statistical test. This range is a range of model outcomes, not a confidence interval. But this should tell you, yeah, it is really humans that did this, right? Now, we have some confidence that these models are not completely crazy, that they have some skill in forecasting the past. This is the only way you can prove skill of a model, right? So let's take these models to the future and see what would happen. Here you see, right? So we start in 1950, reconstructions and observations, and we go to the year 2100. Now the year 2100 for me is science fiction, right? I will not get there. A good few of you guys will see the year 2100, right? It will be much older, but chances are that the majority of the people in this class will see the year 2100. Global warming until today was roughly 1 degree. Depending on the scenario, that may be 1.5 degrees. It may also be 5 degrees warmer. 4 degrees warmer than it is today, right? Sea ice will come down. Again, depending on the scenario, it may be practically ice-free in 3 out of 6, 3 out of 5 of these scenarios. Ocean pH will also come down. We'll talk about that in a sec. Sea level will go up by up to 1 meter or so. This is the same models that I just showed you, right? Let's look at temperature a little bit closer. Observed or projected warming is not homogeneous. This is observed warming of the last century. This is predicted warming of the last century. You see that again. It's not just that we get the global mean right, but also the spatial pattern we get roughly right. And then if the world warms further, 1.5 degrees on average, 2 degrees on average, 4 degrees on average. Now there's two patterns that stand out here. One is that warming is more pronounced towards the poles than towards the equator. And that's fairly basic physics, but I won't have time or energy to explain that. The other thing that you see is that warming over land is much more pronounced than warming over the ocean. And the reason for that is heat content. That the earth ground warms up much faster than water does, right? That is why the seawater is at the moment rather warm, right? At the end of summer. Much warmer than the air. That is why we have sea climates. That is why it never gets really cold in Brighton, because we're close to the sea. That is why in precession of the seasons, the meteorological winter lags behind the astronomical winter. It gets dark before it gets cold, winter time, and in summertime or in springtime it gets light before it gets warm, right? And you see the same phenomenon here. Of course, this matters because the vast majority of people lives on land, not on the ocean, right? So the warming that we experience is much more than the global average, right? That matters. So that is temperature. I talked about if you have higher temperature, then you can have more water vapor in the air, and that means that rainfall patterns will change, right? And here we see simulations, projections of what would happen to rainfall patterns. 1.5 degrees of warming, 2 degrees of warming, 4 degrees of warming. Obviously it gets stronger. What you see is, and this is the global average, the annual average, sorry. What you see is patterns of wettening in blue and patterns of drying in brown. And you see fairly complex patterns. You see also areas I actually don't quite know. I mean, one thing you do know is that if temperature changes and if temperature gradients change, the land warms up faster than the water, then rainfall patterns must change, right? Because pressure patterns have changed. And there must be more water vapor in the area, so it cannot be that rainfall stays constant. You cannot change the temperature and keeping rainfall constant. That is a physical impossibility. But the system is so complex that in many places we actually can't predict how rainfall would change. Now this is important, this is probably more important, and this is how soil moisture would change. Plants actually don't live on rain, plants live on the moisture they take out of the soil, which is an accumulation of rain over the last couple of months, minus the evaporation and the extraction of water, and the movement of water. So soil moisture is actually more important. You see some places drying, some places wettening. Fairly complicated spatial patterns. These are projections of the global mean sea level. This often confuses people. People think, well, it gets warmer, ice melts, and that causes sea level rise. That is true, but it's actually not the most important thing. The most important thing is if the atmosphere warms, then the water in contact with the atmosphere must also warm, and warm water expands. Now you think that's nuts, right? You have a cup of tea or coffee there, right? That is cooling down, but it's not visibly shrinking. right? If you take a cup of tea and you let it cool down, yeah, basic physics says that it must have shrunk, but I don't see it happening, right? So how can it be that if the ocean warms up by 2 or 3 or 4 degrees, we have substantial sea level rise? Well, the answer is very simple. The ocean is very deep. The ocean is on average 3 kilometers deep. So if a column of 3 kilometers expands by a tiny little bit, that looks to us, puny humans, less than 2 meters, most of you substantially less than 2 meters, actually looks like a lot, right? So that is actually what is mostly going on. A tiny expansion of a very big column of water appears to us as half a meter up to a meter of sea level rise, right? Again, the pattern is not uniform. Some places the ocean rises faster than in other places because of redistribution of water, because of redistribution of ocean of pressure patterns, and so on and so forth. Now, and then on top of that, ice may melt and other ice may slide into sea. Again, there's confusion here. If the ice in the North Pole melts, then by Archimedes, that does not change sea level, because this is ice that floats on the water. If the ice on Greenland melts, that will change sea level, because that is ice that rests on land. Similarly, most ice in Antarctica rests on land. Now, the ice of the East Antarctica or West Antarctica is unlikely to melt anytime soon. This will probably take tens of thousands of years. But on West Antarctica, that's actually a big glacier, the best way of thinking about it, that ice may actually slide into the ocean. That it's currently resting on land. In the future it may float on the water, and if that happens, sea level will go up, right? You can test this by getting a glass of Coke, putting an ice cube in, yes, then the Coke goes up, but if the ice cube melts, then it doesn't, right? You can test all these at home. And unfortunately, this is not the end of the story, but I'm almost done. I talked about rainfall, said that some places will get wetter, others will get drier. There's also places like the south of England where the forecast is that it will get wetter in winter and drier in summer. Again, this causes confusion. Some people say because of climate change we will have more droughts and more floods. And then some fools say, you must be crazy, how can it get wetter and drier? Well, it can get wetter in one season and drier in another. And of course, in the south of England, this is the exact opposite of what we want, right? Because we have a drought problem in summer, and we have a flood problem in winter. And in the future, we will have more of a drought problem in summer and more of a flood problem in winter, right? I showed you a graph of ocean acidification, but I did not talk about it. Nowadays, we call CO2 CO2, or carbon dioxide. But the proper English word is carbonic acid. And the operative word here is acid. Again, because of the laws of partial pressure, if you have more CO2 in the atmosphere, then you must have more CO2 in every water body that is connected to that atmosphere. So you have more CO2 dissolved in ocean water. And because it's an acid, this means that the pH falls and the acidity rises. Now, you may have heard stories about bad men throwing acid at women in particular. We're not talking about that sort of acid. This is a very mild acid. It's perfectly fine for you guys because you have your skeleton at the inside of your body. for those species that have their skeleton on the outside of their body, mollusks and those sort of things, this is pretty bad. Because, as you may know if you've ever cleaned your bathroom, the way to remove the little white stains, that is calcium, that are deposits if you run your shower, there's calcium dissolved in that water, the water evaporates, but the calcium stays behind, those are the little white stains. If you want to get rid of those, what you do is you pour on acid, right? All the cleaning products for your bathroom contain acid. Now, if the outside of your body is made of calcium, and if you have a more acidic environment, you don't grow that fast or that much or not at all, right? So this is bad for corals and all shellfish. Not dangerous for you to swim in the future ocean. It's also bad for the cliffs of Dover or the Seven Sisters, right? They will also erode faster. Finally, what I did not talk about is, I did mention it, right? If temperature changes, and if temperature changes differently in different places, then pressure patterns change, and differential pressure changes. And that must mean that your winds will change as well, right? There's no escaping there. Now, we don't care so much about wind in general. We do care about storms. There's some good news, but it's mostly bad news. The good news is that tropical storms, the hurricanes or typhoons, the hurricane that we currently see over Florida, they will not come to us. It is unlikely that tropical hurricanes will ever extend their range far outside their current area. Maybe a little bit on the margin, but not a lot. Another bit of good news is that storms will not become more frequent. If anything, the models say storms will become less frequent. That is the good news. The bad news is that storms will become more intense. There's more energy in the system, temperatures are higher, storms can become more violent. Now, if we weigh that against the good news of storms perhaps becoming less frequent versus storms becoming more intense, it's actually pretty bad from a human perspective. Because if storms become more frequent, that's actually not such a big deal. Because if you have a big storm, then all the vulnerable stuff is taken out. So if a year later you have another big storm, it actually does less damage. But if wind speeds go up, the force that the wind exerts on you or your house or the tree in front of your house is the wind speed to the power 3. So a small increase in the maximum wind speed means a large increase in the force exerted on whatever gets in the way of the storm. And a small increase in wind speed can actually do a lot more damage. And from our perspective, it's exactly that what is going on. Storms will become more intense and will do a lot more damage as a result. That is true for the tropics. It's also true for the storms that hit us, the extratropical storms. Also there, probably they will be more intense in the future and will do more damage. So in 3 weeks' time, we're going to talk about what are the implications of all this. After the break, we're going to talk about where do these scenarios come from. So I have here 5 different colors, and I talked about what is the response of the climate system. After the break, we're going to talk about where did these colors come from? How can we know future emissions? And what are the differences there? Okay, we're going to break for 10 minutes. I owe you two apologies. Yesterday I forgot the name of the new Environment Secretary, Ranul Jayawardena, who is now actually this week sneaking out bad news for the environment because everybody's paying attention to other things. The other name I forgot this morning was Eunice Foote, who is the woman who discovered experimentally that CO2 is a greenhouse gas. And then that discovery was overshadowed by the discussion, why is a woman presenting to the Royal Academy? Anyway, I talked about the science of climate change. I showed you scenarios, but I did not say where do these scenarios come from. So that is what we're going to do in the next 40 minutes or so. Before I can do that, I need to say a little bit more about where CO2 is coming from, and I'm going to give you an analytical tool called a Kaya identity. So this was originally scheduled for week 2. As I said, we did the introduction yesterday, so that helps. And I really hope to free up some time to have a proper discussion of the instruments for emission reduction, which is something that we could not have done in environmental economics, right? Because that option wasn't there for you. So this is where we are. We're getting ahead of ourselves, which is good. So let's start with looking at where do these greenhouse gases actually come from. I'm going to focus on CO2. This is global emissions of all greenhouse gases in the year 2015. CO2 is about 3/4 of it all. A lot from power and heat, from transport, from manufacturing, residential, that's mostly home heating. CH4 methane is around 17%, nitrous oxide is about 7%, and then we have the halogenated gases, right? So I'm going to focus on CO2 because that is by and large the most important greenhouse gas, anthropogenic greenhouse gas. So where does CO2 come from? Well, most of it comes from the combustion of fossil fuels. And this is intrinsic to the system. So what do you do? And most of you will have made a fire, right? So you take a bit of carbohydrate called a log of wood or a bronze or something. What do you do to make a fire? You begin by adding heat, right? You put a flame to it. You set fire to it. Now what that heat does is it breaks down the carbohydrate. Carbohydrates are molecules that consist of carbon atoms and hydrogen atoms, and the heat that you add breaks the chemical bond between the C and the H, between the carbon and the hydrogen. You've lost energy, right? But then the carbon reacts with oxygen to form CO2, and the formation of that new chemical bond releases energy. And similarly, the hydrogen that has now been freed from the carbon also reacts with oxygen and forms H2O, water vapor. And also that new chemical bond, the formation of the new chemical bond, releases energy. Now this is important because the only way to get energy out of fossil fuels is by forming CO2. That is where the energy comes from. So to us as economists, this is an externality. But if you look at this as a chemist or an engineer, this is why you do it. Unlike other environmental problems, like sulfur dioxide, also comes from the burning of fossil fuels. But that is because there's always a little bit of sulfur contained in your coal or in your oil, less so in gas. So if you burn your coal that is polluted with sulfur, you form sulfur dioxide, which causes acid rain. So that is also economically it's an externality. It's not why we do this, and it's a nuisance. We don't want it. but also from the perspective of an energy engineer. If you're running a power plant, then you don't want sulfur in your coal, because that means that your coal plant doesn't work as well, it's not working optimally. But CO2 is why we burn it, right? It's the formation of the CO2 molecule that releases energy. So this is intrinsic. If you want to get the energy out, you must form CO2. Rather, you form CO2 to get the energy out. Now, not all fossil fuels are created equal. What you're looking at here is 4 different types of fossil fuels, and the unit is how much CO2 comes out, tons of CO2 per terajoule, that is an amount of useful energy. If you burn natural gas, it's 57 tons of CO2. If you burn peat, it's essentially very young coal, you get 117 out. So fossil fuels are not created equal. And this immediately implies that you also have a tool to reduce your emissions. So let's look at the United States. This is fuel used in power generation in the United States over the last 20 years or so. We have a little bit of oil that is burned, but less and less and less. We have a lot of natural gas, we have a lot of coal, and then these are hydro, wind, solar, and nuclear. Then blow this up to energy use. You see essentially the same picture. So what has happened since we discovered how to extract shale gas is that in the United States the price of natural gas has dropped very substantially because there's a large supply of shale gas, and as a result people have switched from burning gas to make power to switched from burning coal to make power to burning gas to make electricity. So this is the energy use in the thermal park. This is what happens to emissions. Because coal is so much more powerful, generates so much more CO2 per megawatt hour than gas, you see that emissions have actually dropped quite substantially. Total emissions were around 2,300 in the year 2000 and have dropped to 1,450 2 years ago. Right? A very substantial drop in CO2 emissions from power generation in the United States, all because of the discovery of the mining of shale gas. Right? Fracking, essentially. Now, for those of you who are following the current debate, fracking may be a good idea in the United States. That doesn't make it a good idea in the United Kingdom. The big difference, there's 2 big differences between the US and the UK. One is that fracking is a nuisance. In the US, a lot of shale resources are in the big empty spaces of the Midwest. Whereas in the UK, the shale gas resources are close to where the people are, or in nature reserves, one of the 2, so you don't want to do it there. The second reason that we would never, and Jacob Rees-Mogg was talking about this in Parliament the other day, the other big difference between the US and the UK is that in the UK, everything deeper than 2 meters under your feet, if you own a house, everything that is deeper than 2 meters belongs to the Crown. That is, if somebody comes and drills the gas under your house, the royalties go to the state. In the US, everything up to the core of the planet under your house belongs to you. So if somebody comes and drills the oil, you get the royalties. And it's therefore much easier to convince people that fracking installation on their land is a good idea than it would ever be in the UK, right? Okay, sidetracking. So this is what happened to power consumption, power generation in the United States. This picture starts in 1820, goes to 2010. I have not been able to update this yet. Shows energy use across the world according to different types of energy. So at the very bottom, it's called food here. This is muscle power, human muscle power. In the light green, we have animal muscle power. We have fuel wood for burning. And then we have the free fossil fuels, coal, oil and gas. This is not electricity, this is wind and solar and hydro, mostly hydro. And then finally we have nuclear. And what you see is the enormous expansion over the years. This is in shares, a little bit clearer. And what you also see is, yes, there are transitions. We can shift from one source of energy to another. We can shift fuels. You also see that those transitions take a long time, right? What we've seen is essentially it used to be humans and animals doing all the work. That is what you see here, and most of our heat came from wood, essentially. And then we very gradually transitioned to burning coal, and then we gradually transitioned to burning oil. And now we're gradually moving out of the oil age. But what you see is that, yes, these transitions happen, and there's no reason to assume that in the future we will not have similar transitions. But you also see, well, these are processes of decades, right? This is not, we change from one year to the next. So that is where most CO2 comes from. 75%. Another 20% or so comes from land use change. I talked about the albedo effect. If we chop down forests and replace them with pasture land, then the color of the surface changes. But trees are carbohydrates and grass are carbohydrates, but trees are a lot bigger. So if you replace forest with grassland, you lose a lot of CO2, right? And that is another important source of carbon dioxide emissions. And then finally, about 2-3% of CO2 comes from the production of cement. And again, this is intrinsic to the process. So cement, essentially what you do is you take limestone, and limestone has a lot of carbon in it, and then you heat it up and you add oxygen, and then the oxygen sucks the carbon out of the limestone, and what remains is cement. Right? And then you use that to build stuff. But you don't have, there's no natural cement, you have natural limestone, and the only way to turn lime into cement is to get rid of the carbon. And by far the cheapest way of doing it is by oxidizing that carbon, by turning it into CO2, right? So again, it's intrinsic to the process, which makes it difficult to get rid of it, right? Essentially, you need a completely different production process. You may need completely different material. The second most important anthropogenic greenhouse gas is methane, CH4. And there's 4 big sources of this. One is ruminants. And again, this is intrinsic. So ruminants are cattle, camels, and other hoofed animals. So what these animals do is they eat grass, carbohydrate, and they turn that into meat and milk, right? And the meat and milk is what we consume. Most of you, not all of you. Now, if you look at the chemical composition of grass and compare it to the chemical composition of meat or milk, you would notice that there's less hydrogen in the products that we consume than in the products that the cow consumes. So somewhere along the way you need to get rid of the excess hydrogen. Now cows have done that for a very long time in their stomachs. So essentially they eat the grass and then they have it in their tummy, and then they release the hydrogen, and that is dangerous, right? Hydrogen is a very dangerous chemical. If you have hydrogen in an oxygen-rich environment, H2O, which is a radical, it reacts with everything and destroys everything. So you don't want that. And cows are smart enough not to have a lot of oxygen in their tummies, because it would literally eat them from the inside. The second route by which you can get rid of free-floating hydrogen is to go from H to H2, hydrogen gas, which is what makes zeppelins float, right? So if cows would do that in their tummies, that would not be a smart strategy either. So instead, they have formed a symbiotic relationship with methanogenic bacteria, and those bacteria turn free-floating hydrogen, into CH4. And this is chemically the cheapest way of getting rid of the excess hydrogen. So they sacrifice essentially one useful atom of carbon to get rid of 4 useless or dangerous atoms of hydrogen. And then you have CH4, and unlike popular belief, that comes out at the front. They burp it out, right? That's where most of the methane comes from. And this is again intrinsic to the production of food and meat. There's another animal that occupies a very similar ecological niche as cattle do, and that's the kangaroo. And kangaroos do not produce methane. They instead produce acetate, which also gets rid of the excess hydrogen, and they poop that out. But that is innocent, right? Essentially what I'm saying is that if you really want to get rid of all the methane of cattle, then what you need to do is genetically engineer the metabolism of a cow to be the metabolism of a kangaroo, right? That is how difficult this is. The other second main source of methane is paddy rice. That is rice that is grown on the water in irrigated fields. Similar story. If plant material decays, rots in an oxygen-rich environment, it turns mostly into carbon dioxide. But if it decays in an oxygen-poor environment, underwater, then it goes to methane, CH4, right? So if you grow rice in an irrigated field, in a flooded field, and then the leaves of the plant drop, they drop underwater and they go to methane. In English, we used to call this swamp gas, right? Essentially the same thing happens in swamps everywhere. Paddy rice is the most productive crop. If you have a small plot and you need a lot of calories from that plot, then your best bet is to grow rice in a flooded field, right? Getting rid of this is very, very difficult. Telling people to eat less rice is also very difficult because a lot of people who eat mostly rice are very poor. Waste is another source of methane. Same story. We throw away a lot of stuff. We throw away a lot of food stuff. We throw away a lot of organic stuff. If that ends up in a landfill with other waste pooled on top of it, then it's an oxygen-poor environment, and that organic stuff can only go to methane, to CH4. Now, strange story. CH4 I called methane. That is if we don't like it. If we like CH4, then we call it natural gas. The two are the same chemically. If we like it, we call it gas. If we don't like it, we call it methane. Now, there's a lot of gas being used, mined. Whenever you mine coal, there's always pockets of gas that you just vent into the atmosphere. You must have seen flaring. Whenever you're drilling for oil, there's always gas that comes up as well, but then typically that is burned. Those are the flares that you see at oil fields. But also if you drill for gas, then not everything ends up in the pipeline where you want it to be. And also if you transport gas through a pipeline, then some of it escapes because those pipelines are never perfect. And then occasionally somebody comes along, and we still don't know whom, that blows up two of the big pipelines, right? And you have a lot of methane escaping. So that is another source of methane. So that is where that stuff comes from. And nitrous oxide, N2O, you may know it as laughing gas, right? You may have consumed it on a Friday night. It makes your voice squeaky, and it changes your perceptions of things. Perfectly innocent for human consumption. But it changes the climate. And nitrogen oxide mostly comes from the over-application of fertilizers. So one of the things to make plants grow faster is to pour on fertilizers, and one of the things that plants are always short of is nitrogen. Then you pour on the nitrogen, but farmers are risk averse, and fertilizers used to be cheap, so they pour on too much fertilizer, and then the excess goes through a series of chemical transformations in the soil to nitrous oxide, N2O, and that is another greenhouse gas. And then there's this whole bunch of other gases that we can talk about for a very long time, but as I said, they are very small. We'll get back to them in week 10. That are essentially specialized industries making semiconductors, as coolants and refrigerants, those sort of things. And some of them leak as well. So that is where it comes from. And some of these problems you think, well, this is relatively easy to solve. And some of these problems you immediately say, well, this is actually going to be hard to get rid of, right? I mean, methane leaking from landfills, it's just a matter of putting a cap on those landfills and capturing the methane as it comes out, right? Expensive, but doable. Convincing hundreds of millions of rice farmers to do something else, most of them informal, in the informal economy, that is a hard one to do, right? Okay, I promised I was going to talk about scenarios, and that's what I'm going to do, but first I need to talk about the chi identity. I have 20 minutes left. So, if you want to know where is CO2 emissions going, that's not English. You first need to ask, where did CO2 emissions come from in the past, right? So from the period 1965 to the year 2021, I think, this is global CO2 emissions from fossil fuel combustion. And everything is indexed to be 1 in 1965. And what you see is that over this period, 55 years, CO2 emissions tripled, slightly more than tripled. And the question is, where does this come from? Now, one way of answering this question is to use the Kaya identity, which you see here. It says that emissions E equal the number of people, P, times per capita income, Y over P, times the energy intensity of the economy, X over Y, times the emission intensity of the energy sector, E over X. Now this is true, right? P cancels against P, Y against Y, X against X, so this identity really says that emissions equal emissions. It's an identity. Identities are always true. All identities are true. Some are useful. This is a useful one. So what does this tell you? That if you want to understand trends in CO2 emissions, you should look at population growth in blue. Number of people over this period grew by about 150%. Emissions tripled, right? So that means that emissions per capita went up over this period. Income grew by slightly more than 150% on average on the planet. Now these two trends multiplied, 2.5 each makes a growth of 5, right? So the world economy over this period grew by a factor 5. Emissions grew only by a factor 3. So the emission intensity of the economy has fallen over this period. Why did it do so? Energy intensity, how much British thermal units or terajoules or megawatt hours we used, or tons of oil we used to make 1 pound of value added. Over this period fell from 1 to, what is it, 0.65? So we've essentially generated more and more income for every unit of energy over this entire period. And then the final component is, so what energy did we use? And what you see is a slightly wobbly trend. That is the purplish that you see here. It came down. This is the oil crisis, oil crises of the 70s. It came down, and then it sort of stabilized, and it came down, and then China and India started growing, and it went up again, growing by burning lots of coal, and now it's coming down again. Most of the action was actually in improvements in energy efficiency rather than in fuel switching, right? Now we have a rough understanding of where do these CO2 emissions come from. We don't just have the trend, but we also have an understanding of this trend. And what we can then do is take these trends and project them into the future. And then you see pictures like this, and the different colors that you see here are different projections of how many people there will be in the future, how rich they will be, how much energy they will use, and what sort of energy they will use. And obviously that is very uncertain, and you can have very different views on that, and those are the different colors that you see on this. And then the bars, or the confidence intervals, or whatever the areas that you see around that, that is the uncertainty of the climate models. Whereas this difference is the uncertainty about our future emissions, right? Which is actually more important than our uncertainty about the climate models. Now, the Kaya identity, you may have guessed, was named after Yotzi Kaya. And essentially we can use this to explain things in the past, but we can also use it to project things into the future, right? And if you want to know how much CO2 will we emit, you need to know how many people there will be, how rich they are, what energy they use, how much energy they use, and what energy they use. But if you then take it to methane, you also need to predict how many people there will be, how rich they will be, how much meat they will eat, and what sort of meat. What I did not say is that chicken is very different than cow's meat, right? And this makes it a hard task, right? You've all done macro, you know how difficult it is to predict economic growth. But that is what we need to do if we want to understand future emissions. Now, that is hard, 12 minutes left, but people have done it. And these are the lines that I showed you before. In one of the earlier graphs, you had these abbreviations, SSP 125. Well, these are the SSPs, again, shared socio-economic pathways, developed by a consortium better known as NOT, the Intergovernmental Panel on Climate Change. And here we see those scenarios broken down by their components of the chi identity. So to start at the top left, number of people. 1970 to 2020, that is observation. The scenarios are slightly older, so you actually see deviations starting around 2010. It's because they haven't been redone and recalibrated. That is why things start to diverge earlier than you would have expected. There's essentially three scenarios there. A fairly optimistic scenario in terms of number of, fairly low scenario that says that the world population is going to peak at around 8.5 billion and then come down to 7.5 by the end of the century. A scenario that is in the middle, where the number of people peaks at around 9 billion and stays there, and then another scenario where the number of people keeps growing and growing and growing and hits 13 billion by the end of the century. This is very important, right, because this essentially determines the size of the economy and everything that comes with it. Now, these population projections are actually difficult to do and uncertain. You may think, well, this is a relatively easy problem, right? Because we know how many people there are on the planet. There's actually a website where you can see to the very last digit how many people there are on the planet, which is nonsense, right? You go to a country like Nigeria, they don't know how many people there are in Nigeria. That's a rough guess, right? Actually, we don't know how many people there are in the UK because our registration is non-existent, right? This was something that was invented and introduced by Napoleon, and we were never occupied by Napoleon, so we never introduced a proper population registry in this country, and we have these censuses that are imperfect, and we have some interpolation in between. We don't know how many people there are in the UK, let alone that we know how many people there are on the planet, right? In the year 2020, but we're actually projecting that into the future. Now, you may also think, well, that is a relatively easy problem. Because, I mean, look around this room, you're all in your early 20s. I know how many people there are. Chances are by the time you're 40, and most of you are parents, right? So that is relatively easy to predict for a population, not for you guys individually, how many children will be born given that we know the population structure now. And you guys will have children in 10 years' time, and then your children will have children in 40 or 50 years' time, right? That's an easy prediction problem. The difficulty and the main difference between the three scenarios that you see here is we don't know how fast fertility will decline as people grow richer. Predicting mortality is relatively easy. That's a pretty steady trend that keeps going down and down and down and down. Fertility is actually a pretty hard thing to predict. And that is the main difference between these three scenarios. It's actually mostly the women of Africa have 2 children in 30 years' time, or 3 or 6, right? That is the main uncertainty here. Now, second component of the chi identity is how rich will the average person be? And you see that there's 5 clearly distinguishable scenarios here, right? Which is strange, right? Which is very strange. Because fertility and mortality depend on income. So how can you have 3 population scenarios and 5 income scenarios? The reason is very simple. These guys were afraid to talk to these guys, right? It's as simple as that. There's no feedback from this component to that component. What you also see is fairly rosy pictures of where the future economy is going. So the current or the average income on the planet is around $7,000 per person per year. Average. That will go up in the most pessimistic scenario to 21,000, which is Portugal. In the most optimistic scenario, it will go up to 140,000. That's Bermuda. That's richer than Luxembourg. Now, the problem with these projections into the future is our lack of imagination, right? If we asked people 80 years ago to describe how rich we would be in the year 2020, they would have absolutely no clue. And even though you guys are relatively poor, compared to the people 80 years ago, you are enormously rich, right? There's now no consolation, right? And therefore it's very hard for us to imagine what the economy in the year 2100 would be like. An average income of 2100, an average income in the year 2100 of 140,000. This is the average, right? That means that there must be so many multi-billionaires, probably a few trillionaires around. It's very hard to imagine what that world would be like. This world is much easier to imagine, right? Because this is well within the range of observations. Still, you may wonder, why are they all going up? Why is the most pessimistic scenario a tripling of income? A tripling of income. The reason is, again, human folly. These are scenarios that come out of the United Nations, and you can't go with a scenario to the United Nations and say, sorry government, your growth projection will not come true, and you may just live in a stagnating economy, or in the UK, completely faltering economy. That is just not something that any government will ever approve, right? So the only thing they could get through the United Nations process is growth, economic growth everywhere. So that is what we have. Energy intensity, carbon intensity. Energy intensity, here you see the historic trend. It's falling, falling, falling. Actually, if you push this back, you can actually push this back to Babylonian times. And it's always been falling. I'll talk about it more next week. The projection is that it will continue to keep falling. The reason for that is very simple. Energy is a cost. If you can do something to get more money, more pounds out of the same unit of energy used, then you would do it, right? It's in everybody's everybody's interest to minimize the energy cost. So the projection is that it will keep falling and falling and falling. Carbon intensity, how much CO2 comes out of our energy system. They've actually been mostly stagnant, right? It goes up and down and up and down a little bit, and world average. The projections are mostly falling, but some are going up. And the very high emission scenarios that you saw and the very high temperatures are actually coming out of these scenarios where CO2 intensity does not change much or may even increase. Now you need to think about what does that mean, right? Essentially this means that for CO2 intensity to increase, we need to stop using solar and wind, and we need to stop using gas and start burning more coal. That's the only way to increase your CO2 intensity, and some projections see this happen. Other people say, well, this is completely bonkers. Because we're not running out of coal, but we're definitely running out of cheap coal. And if you look at the relative price, the price of solar and wind, that is coming down very rapidly. And it's very hard to imagine that solar and wind will ever become more expensive than coal again. And therefore there's just no economic sense, as far as I can see or many other people can see, of these scenarios where we increase the amount of coal again. There may be geopolitical reasons to do this. That if you have a China that turns inwards, that it uses its domestic coal reserves rather than import oil and gas. But then also there's a lot of wind and there's a lot of solar in China, so why would they do it, right? But these are the scenarios. As you may have guessed from the way I talk about this, these are strange numbers, right? This is a strange set of numbers that came out of a very strange process. But it's the only scenarios we have. And this is where all the climate projections that you hear so often in the media, or the climate impact projections, climate change impact projections that you hear about in the media, it all is based on this kind of work. Okay, that's it for today. Next week, I'm going to take the Chi identity a little bit more and use it to talk about options for emission reduction and the costs of doing so. Okay, I see you next Wednesday.